We are quite often asked two questions. The first question is, what is NLEC, or what is nonlinear error correction? The second question is, what is the difference between NLEC, nonlinear error correction, and SLEC, segmented linear error correction? To answer the above two questions, let's first look at the simplest form of error correction, which is LEC, or linear error correction. LEC, linear error correction, is where standard length, in this case 120 mm, is placed parallel to the machine axis being calibrated. The standard length is then measured by the machine, and the difference between the standard length and the measured length is entered into the machine's readout or computer system as calibration data for that axis. The problem with this type of error correction is that a large error curve can occur across the length being measured. In this case, the standard length of 120 mm, the greatest amount of error is halfway across at the 60 mm portion. This is the most problematic type of error correction which is in use today. SLEC, segmented linear error correction, is where segmented length is placed parallel to the machine axes being calibrated. This segmented length can be a step gauge, stack gauge, or as in this case, a glass slide with certified chrome on glass markings. Each segment is then measured by the machine being calibrated. The difference between the certified values and the measured values of each segment is entered into the machine readout or computer system as calibration data. As you can see, there are smaller calibration errors with SLEC, segmented linear error correction, than they are with LEC, linear error correction. The only drawback to segmented linear error correction is that it does not take squareness into account on machines with multiple measuring axes. NLEC, nonlinear error correction, is where a glass plate is placed on the stage of a machine being calibrated. This glass plate has chrome on glass lines arranged in a grid pattern, and each intersection point of these lines is certified back to a known standard. We then measure each intersection point, and the difference between the certified values of each intersection point and the measured values are entered into the machine readout or computer system as calibration data for the stage being measured. This is done both in the X and Y axes at the same time. Notice how the error curves only go halfway into each grid square. This is because the opposite intersection points also have an effect on the error in the grid squares. This is done for all grid intersection points, creating a far more accurate calibration for the machine's measuring stage. How does NLEC, nonlinear error correction, help in a real-life measurement scenario? Let's take a standard length, in this case 80 mm, and place it diagonally on the machine stage. On this standard length, we'll take 2 points, one at each end. Since the computer system or the machine cannot actually see the standard length being measured, and for the purpose of this illustration, we'll remove it. The computer then looks at each of these 2 points and calculates the X and Y values of these 2 points back to the machine's home position, 0, 0, usually in the bottom left-hand corner of the stage. The computer, once calculated out the distance of each point from the machine's 0, 0 point, then can calculate out the difference in both the X and Y axes of the 2 points. With this information, The computer then can apply a simple mathematical formula to calculate out the length. The formula to be used will be c equals the square root of a squared plus b squared, or c would equal the square root of the x-axis 58.978 squared plus the y-axis of 54.032 squared. C would equal 79.986. Obviously, this is in error. Remember, the standard length we started out with was 80 millimeters. Now, we'll do the same calculation again, but first, we'll apply nonlinear error correction, NLEC. Nonlinear error correction works on each point. What it will do is look at each point within the grid square it resides in and adjust the point values by the interpolated errors. After this is done, the computer can then recalculate the difference between the x values and the y values of each point. After this is done, it can apply the same formula again. C equals the square root of a squared plus b squared. So, in this case, c would now equal the square root of the x-axis of 58.983 squared plus the y-axis of 54.046 squared. C would then equal the square root of 6400, which equals 80 millimeters. Remember, 80 millimeters is the standard length we originally started out with. This is how nonlinear error compensation is applied in real-life scenarios.